Okay, so again, thanks everybody for joining for the Learning Lab 10. I'm gonna share my screen and start the presentation. Okay. Okay, so that's the presentation that we're gonna be talking about today. It's an overview of machine learning applications on the energy sector. So it's being prepared and presented by me and Daniel Tread. So we are the hosts. I'm Marcelo Guarido, and I'm a data scientist with a PhD in geophysics. And nowadays, I'm at the head of the data science initiative in Cruz. So Daniel, would you like to present yourself?
Yeah, I'm Daniel Kral. Welcome everybody for this new session of seminars. And I work in university, and I'm just helping Marcelo with these webinars.
Yeah. So David Emery is gonna also start to be co-host for the next labs. So it was just a fast decision. So you'd like to present yourself, Dave?
Hello, I'm David Emery. I'm retired from Husky Energy and been helping at Cruise and hope to start a PhD in the fall with Daniel Trant.
Okay, thank you, Dave. So we are all part of the cruise. It's a consortium at the University of Calgary, and we are also part of the Cruise Data Science Initiative. That's a new initiative inside Cruise, where we're going to be focused on a machine learning project for the geoscience and also academic and industry projects. We also have programming training, like in R, Python, and MATLAB, also for applications in your area or your company. And we also provide those learning labs that those are bi-weekly webinars where we do hands-on presentation in how to use machine learning and data science and those type of softwares like R, Python, MATLAB to work with your data. If you want, you can access all the information that you want from the Cruise website in the Cruise Data Science Initiative tab. You're going to see all the information from the lab from the last year. You can access all the material and all the files from last year. Um, so today, what you're going to be talking about is going to be the first lab of the year, and they're going to be changing how the lab is going to work compared to the last year. So last year we were more focused on the oil industry, but this year we're going to also be included renewable and wind energy. We are doing that because cruise is starting to grow, and also we are looking for new partners and new type of projects that are going to be related to the clean energy and all related to machine learning. And that's quite important for us to know because recently there are a lot of companies that are working with that and hiring data scientists to work with artificial intelligence um, to optimize their forecasting and the production for any kind of energy. So most of those companies are for clean energy. We also have some oil companies, big ones like Chevron, Shell, British Petroleum, Total, Eni, Exxon, among the others that are also starting to invest on renewable energy. There is a very interesting one, this M Cloud. I just included it here today, this one. And we just saw the news yesterday that they are coming to Calgary and they wanted to make their headquarters here in Calgary. So if you click here, you're gonna see their website and how they're working. So they work with uh, renewable and clean energy, mostly for wind energy and how and they have the careers, so we can check. So they're gonna be hiring a lot of people here in Calgary for the next month or so. So that's how it's gonna be divided, the presentation today, in 4 parts. In the first one, you're gonna see some examples in machine learning for energy consumption and price. So those are gonna be machine learning techniques to analyze and forecast energy consumption and price, among the other applications. The second one, we're going to talk about the oil and gas. Still a few examples, how the machine learning is being used to help the interpretation decision-making in the oil and gas industry, and also in the renewable energy, how machine learning is used to optimize the use of a renewable resource. So they are really related to weather forecasting. In the end, we're going to explain how the learning sessions are going to happen this year, how the learning labs. So this first one is not going to be hands-on because we're going to be talking about different applications. And for the next one and on, we're going to be working on hands-on. The plan is to get one of those papers or papers that are not here listed today, and they're going to be trying to reproduce their methodology. But I'm going to explain better by the end of the session today. So that's just a quotation for Andrew Ng. So Andrew Ng is considered one of the fathers of the deep learning. And I like this quotation that he says that just as electricity transformed almost everything 100 years ago, today I actually have a hard time thinking of an industry that I don't think artificial intelligence will transform in the next several years. So he's saying that it's impossible today for a company not to have a data scientist working with artificial intelligence and machine learning there to optimize the work. Okay, so let's go and start doing the presentations. We're gonna now start to see a bunch of papers that I'm gonna say that I read a lot of papers and selected some that I found they have some interesting methodologies that you're gonna be trying to reproduce during the year. So we're gonna start about energy consumption and price. So it's gonna be a combination between oil and gas and renewable energy. And the first paper from Kem et al. It's this machine learning based approach to predict energy consumption of renewable and non-renewable power resources. So the goal of this paper was to get all the information they have for resource of energy that they have in South Korea. And they used an island named Jeju in the south of South Korea as a test lab because they are planning to change all the source of energy from non-renewable to renewable by 2030. And the goal is to forecast how much energy is going to be needed in the next years so they can plan better how they're going to be doing this replacement. So so they use different sources of electricity in South Korea, and they have the regulator there and different companies that provided fossil fuels electricity, resource from fossil fuels, and also they have the renewable ones like the photovoltaic, that's solar energy, the wind power, and the BTM. BTM stands for behind the meter. Those are solar energy that doesn't have a contract. Basically are just solar cells installed in some houses that can go to the circuit. That's how they measure, and they're going to be doing their forecasting. That's the total energy demand that they need in the Jeju Island in blue for the non-renewable sources and in green for the renewable sources. They have different scales in here, but in both scenarios, they are demanding more and more energy. And what they want to do in the future is to increase the slope of the demand for the renewable energy. So they're going to be doing a forecast of how much energy is going to be necessary by just summing those two energies, these two amounts, these two plots, and try to predict for the future. And what I think it was interesting in this paper is the machine learning model that they are using. They are using something called a hybrid model where they combine different machine learning algorithms. They are using the CatBoost. The CatBoost is a library in Python for gradient boosting, the support vector regression, and a multi-layer perceptron, that's just the neural networks. They calculated the forecasting for each one of those models, and then they use a volt system to do a final forecasting, probably a voltage a voltage system over the probabilities of each one. And they combine these three modules to create a hybrid forecasting. And what they do in the paper, they compare against other methods or other models that are not hybrid. Those are the results that they got for the forecasting. The blue one is the actual value for the June 2019. And the black one are the predictions using this hybrid model. It's quite precise. There is this weird effect to be overestimating by the end of the month. Apparently, this is increasing the amplitude over time, but then that's something that they need to look at. And when they show their metrics compared to different machine learning models, the proposed one got best metrics because they are the metrics that they're using is mean absolute error and the root square of the mean squared error. So shorter the number, smaller the number, better the metric. So they're getting better results compared to very used but single models. The second one, paper, that I found really interesting, it's actually not doing any prediction, but also seeing the relationship between the variables, is this paper by Magazzino et al. It's a machine learning approach on relationship among solar and wind energy production, coal consumption, GDP, and CO2 emissions. So they want to use all those information from 3 different countries, USA, China, and India, and see if there is any causal relationship between them. Because sometimes you can find correlation, but correlation not necessarily means causation. Correlation, it's necessary to be a causation, but it's not enough. So that is even this is small comic here that I like explaining what is correlation and causation. So what they are doing in this paper, they study these 3 countries because they are the 3 countries that has the highest investments on renewable energy, but in counterpart, they are also the highest ones in the CO2 emissions. So they're going to be using a method called Markov blankets. So this is a graph representation where you have different variables, and then you calculate the weights that measure relationship and causation between them. You're not going to go into the methods today. That's going to be when in the future we're going to try to reproduce them. And in the paper, they got very nice relationships. Some are quite straightforward, but some interesting observations as well. The first one is that there is an apparent unilateral causality between GDP that stands for the gross domestic product, and the CO2 emissions. When you say unilateral causation, that means that a country with higher GPD or GDP causes higher CO2 emissions, but a country with high CO2 emissions not necessarily has a high GDP. There is also a bidirectional causality between the GDP and the coal consumption. So let's remember, when you say coal consumption, is the coal consumption for electricity generation. So that means that a higher GDP, higher coal consumption for energy, and higher coal consumption for energy, higher GDP. I make sure to say that for energy generation, because there is a report from WHO saying that country that's having economic crisis has an increasing. They have an increase in coal consumption by the population because they stop having access to electricity or other means, and they have to use coal to cook. So that's why I'm going to say coal consumption for electricity generation. They also saw that there is no apparent cause effect of wind and solar energies with CO2 emissions. That's quite straightforward. Only India showed some correlation, but they told that's due to equipment construction and also to drying peat bogs. For people that doesn't know what a pit bog is, pit bogs are dry lands, or sorry, are wetlands that have been formed in the last thousand of years, and all the dead um, plants, they go to the bottom of these uh, pit bogs, and they create a layer where it doesn't allow the CO2 to pass through. So they are actually, there is a reservoir of CO2 here. So in India, they are building those renewable energy um, plants in those areas because they are not good for any kind of production. And those areas are drying and they are actually releasing the CO2. They also saw there is a strong causal effect of coal consumption and CO2 emissions that looks straightforward. And knowing this information, they can forecast the CO2 emissions with high accuracy. And the last paper for this first part, it's a very interesting one for the oil price forecasting. So it's a text-based crude oil price forecasting, a deep learning approach by Lee in 2019. And what they are proposing in this project is how to predict the price of the oil that it's quite volatile. Usually they use the historical information of the price plus information from supply and demand. But what they're including in here, they're also including some news information that they get from the crude oil's news column from this investing.com. So they are getting uh, what the journalists are talking about and see if those can create some change points or and improve their forecasting. And they use this combined information to do a forecasting. So what they're doing here in their methodology, this top part here, it's all a natural language processing step where they get those news from the internet. So they do a data processing where they separate words by tokenization, do some filtering, removing stop words and term weighting, which words are more important. They do some sentiment analysis and convolutional neural network classification. And then they do a LDA, that it's a clustering method to divide those words into topics. So they want to see if the news that has those words, if they belong to a specific topic. And they're also going to be combining with the historic price of the oil and financial market data to create a large data set and to predict the oil price. Unfortunately, they didn't show a very nice plot of the forecasting, but they did very nice observations. The first one, when they applied the LDA for the topic analysis, they could find 4 different topics in the data set among the using the words that from the news. And in the first topic, in bold here, they separated some very interesting words. In the first one is the natural gas, weather, warm. So they say that this first topic is related to natural gas production and selling, and also for weather information. The second topic, that is this crude oil supply dollar euro. So they say that this is related to the crude oil production and also to the supply and demand. The third topic, they see these countries here. So they're relating this topic as political topic. And the last one, by those words, stocks, trade, composite, they say that it's related to the stock market. So just by doing a clustering, that's unsupervised learning, they could separate the topics of the words, and that's going to be helping them to understand the news and how to do the predictions. Again, they didn't show a plot of the predictions, but they showed they tried 3 different methods: the random forest, support vector regressor, and linear regressor to do the forecasting. And they are showing some metrics: the mean absolute error and the root square of the mean squared error. And they showed here when you are using a combination of 1 plus 2, where 1 is the text features and 2 the financial features, you got better metrics compared to only using financial features. If you only use the text features, you're not getting a good prediction. You get a better prediction using only financial features, but when you combine both, you improve your prediction. Only for the linear regression that you lost, you made it worse, probably because this is a linear forecasting, where the support vector regressor and random forest, they can be nonlinear. So those are the resources from the first part. Remember that they're going to be available from 1 to 2 days in the Cruise website. So you're going to be able to download this presentation, and then you can just click here and you can go and have access to each one of those papers. So the second part is about the oil and gas and how the machine learning is helping in the interpretation and decision making. So the first one, I got this example, a machine learning methods in geoscience by Manier and others from 2018. I just selected this paper because they actually show 2 different examples. The first one here on the left, they are doing a well log correlation work where they are using gamma ray and resistivity, the triple combo, to predict where are the tops here in the logs. And the second example, they use 2D seismic data and the image segmentation method to predict, to try to detect faults in seismic images or in seismic sessions. We actually do this job also in Cruise. So if you wanted to learn more, you can talk to me, to Daniel, or Dave, any one of us. And we are using actually a 2.5D approximation. So for the first one, that is the correlation between the logs to try to predict the tops, they are using a neural network methodology where they are combining a fully connected layers with 1D convolutional neural networks or convolutional layers. And they are using training a data set where you have the tops marked, and then they apply these and try to predict the tops from a new log down here, from a test log. What I'm looking here, apparently the predictions are not doing so well as they expected, so there is a lot of room for improvement. So maybe you can, in the future, take a look into that and see what we can do. The second example is about image segmentation to identify faults. So they use this UNet style model of a convolutional layers concatenation with an encoder and decoder, and they are trying to predict pixel by pixel of an image or a seismic session, what is and what is not a fault. And they're getting actually quite good results. If you look here, we have in red here the true position of the fault, and the green are the predictions. And we might be looking into that in the future. As I said, in Cruise we have this work, and we might be able to show how we are doing in the future labs. Another one that I found quite interesting is from 2017, Ken Smith's paper, Machine Learning Assisted Velocity Auto-Picking. I found this interesting because it's the only one that I saw for the predictions that they use unsupervised learning. They are using a near-to-neighbors methodology to help in the semblance picking to try to get the velocity picked velocity. And that's how it works. They have a semblance and they have a guide velocity, this one in yellow, draw in this one. So they use this guide velocity to help to pick, to do this auto picking of these data points. That's the blue ones. Basically, they are just picking the higher values in some areas. And then they do nearest neighbors to find clusters. In here, they separate the data into clusters. And each one of the centers of this cluster is going to be considered as one picking. So the clusters, centroid, is the peaking. Those are some of the results that they got. This is the machine learning auto-peaked compared to different methodologies commonly used in the market, in the industry. And they claim that the machine learning auto-peaked could get a higher resolution and better continuity between the layers. So you have more lateral continuity where they have these arrows pointing here compared to any other method. So that's one of the methodologies that you might be able to try to replicate. Another one for decision making, it's a data-driven production forecasting using machine learning by Banerjee and others in 2018. So what they are doing here, they are using information of production from a well that's producing oil and gas, and try to predict in the future how it's going to be the production for those wells. So that's very nice to help the owners of the well to make a decision to stop, to drill new wells, and so on. And they are doing this for existing wells, how it's going to be the near future for the existing well, and also for a new well, a place where you don't have a well, but you have closed wells there with similar geology. So I'm going to try to predict how it's going to be the production in a well that doesn't exist there yet. For existing wells, they're using the production rate or the history of the production, plus some information from the well, like the tubing, head, and pressure, to do the prediction. And when they're using for new wells, they use the same information plus a geological map, but not for the well because it doesn't exist. They're using for adjacent wells of that location. So they compare their results for a new well. They get a well that has actually production, but they don't use for training. They use this well as their blind test. And for that, they are using neural networks to do the forecasting. So this is a regression problem. So for the forecasting for existing wells, those are the results of one of the wells they had. The blue ones, the blue points here are the actual data for the production. The orange ones are the predictions on the training area. They use it until this point here to be the training points for to train the model. And the green ones are the predictions in the future, where the model never touch. Those are the actual predictions for the testing. So they are quite reliable, they are quite robust, the predictions, and I would say that they are doing a very good job. Those are some examples from different wells as well for other 4 wells. Actually, for other 3 wells, this one is the same as this, and in all of them, they got very nice predictions. When they go for new wells in a place where theoretically a well doesn't exist, these are the predictions compared to their blind well. Remember that this well here never entered for the training. They are just comparing to see. And in green, there are the predictions. And again, they are quite precise. They are surprisingly precise. So that means that you can use adjacent wells to decide where you're gonna drill your next well. Those are examples for 2 other wells, and all of them, they got very precise forecasting. And in this one, they are just comparing their forecasting with common software used in the industry, where they usually do some linear forecasting. And the green one is the neural network, the one that they are proposing. And I can say that, in my opinion, I believe the neural network is being more robust, and I would trust more this prediction than the other ones provided by common used softwares or software. So that is another one for production forecasting, another paper. I found this interesting, the way they are selecting the parameters. So the name is Application of Artificial Intelligence to Forecast Hydrocarbon Production from Shale by Panjan and others, 2018. And they are comparing 3 different machine learning methods, actually 2 different machine learning methods, the support vector machine and the neural network, with one that's common used in the industry. That's the response surface model. That is a quadratic fit of the production. And in this paper, they didn't use real data. They used the simulations of production with some information that they had from geology and other informations, and tried to compare those three methodologies. What I found quite interesting in this paper is how they are selecting their hyperparameters and their best model. They are using this particle swarm optimization. This is originally a method that was presented to understand the movement and the position of birds, of a flock of birds that are feeding. So they are using these to make the hyperparameters. What they call a particle in this one should be one bird, or in this case, it's one model being trained, and they update here the position and the velocity of the bird. What I understood that could be the update of the hyperparameters of the model. So in this first loop in here, they train one model, could be the neural network, several times. So apparently they are doing that with different random seeds or different or with a cross validation. They didn't make that clear in the paper. And they get what is the best model in this situation, and then they update the hyper parameters and try again until they get the best global solution in the combination of all the random seeds and the hyperparameters. I put here also this draw from their paper of the neural networks that they are using, just to show what are the input parameters that they are using for the forecasting and what they are predicting. They are predicting the oil recovery, the gas recovery, and the gas oil ratio. And down here, it's just a representation of how many parameters they are changing in this particle swarm optimization. And those are the results that they got. In green here are the RSM, the quadratic fit. The blue is the neural network, and the red is the support vector machine. This is a cross plot between the true values and the simulated values, or sorry, about the predictions and the simulated values. And in all of the cases here, the RSM apparently is doing a better job, a quadratic fit is doing a better job than any one of the machine learning methods. The machine learning models, apparently they are underestimating the value of the production in all of those tests in here. And here are the metrics for the R-square and the mean squared error. So in all of them, for the training and for the test, the quadratic fit is actually doing a better job. So what you might be trying to do in this paper of the future is how to do a grid search for to select your parameters, your hyperparameters. The last paper that I'm going to be presenting for the oil and gas is this porosity prediction using machine learning by Chang and others. And one thing that I found interesting is that Brian Russell, it's one of the co-authors, and apparently he's attending here today. So if I say something wrong, please correct me. So what they are doing in this paper, the proposal, is to predict the porosity using seismic data. So they use two different data sets to see how their models are working. One is a synthetic data set that was built using the VP, VS, and density information from one geologic area, and another one from a real seismic data. And they compare in an area where they have a porosity log. Their proposition is to do a spectral decomposition of the seismic and the porosity logs, so they are in an equivalent frequency band. So they do the predictions for porosity for each one of those frequency bands, and they do the summation in the end. And they do that by comparing three different machine learning methodologies: the support vector regressor, the random forest, and the neural networks, or multiple layer perceptron. And they try different input parameters as well, or input features. The first one is just the conventional seismic attributes, or just a seismic trace. The second one is a combination of the seismic trace plus the spectral decomposition. Then the only spectral decomposition, and the spectral decomposition with narrow frequency bands. So for the synthetic simulation, when they use for the synthetic data, apparently doing these conventional seismic attributes plus the spectral decomposition got better metrics in overall, only for the the neural network. For the spectral decomposition with narrow frequency bands, they got a better metric. Actually, the best metric in this table is using these narrow frequency bands and using neural networks. When they go for the field data, trying in the same way, now the spectral decomposition with narrow frequency band worked better for all the models. And now the best model in this situation is the support vector regressor, apparently. It would be nice to understand why this is happening, why in one data, these input parameters are better, and for the other model, those input features are better. But that might be related to the frequency of the data in the beginning. But it would be nice later talk to Brian and see what happened. So those are the resources from this part. And the third part now, we're going to be talking about renewable energy and how machine learning is used to optimize the renewable resources. So you're going to see that they are quite related to weather in general. The first paper, it's this one named the Wind Power Forecast, based on daily wind speed data using machine learning algorithms by Demoli and others from 2019. So this is a project done in Turkey. They had different stations in here where they calculate the wind speed and what was the response in power. And they used this one as their blind spot. One of the things they noted that the model that they created in here that could be trained only with these stations or only with these stations, doesn't matter, is independent of the location. So if they train here, they can apply here or here. If they train here, they can apply in other area. So apparently those are very robust ones. And the goal of this project, they want to understand which area they have a best wind forecasting that could be used to generate energy, because this is a plot of the wind speed by the power that is generated by the wind speed. So there is a minimum wind that you need to have to start getting power, like 4 meters per second. But if you want to have a profit, because those are still business, you need to have more wind every day to generate, but not too high wind as well. Cannot be too strong. Here they have like a limit for this, but in reality, eventually this is gonna drop, because if the wind is too fast, they need to turn off the turbine. So those are the predictions that they actually got using lasso, nearest neighbors, the actual boosting, that's a gradient boosting, support vector regressor, and random forest. And for that blind spot, those are the power that would be produced for each one of those days in 1 year. And it's quite precise. And it's actually really precise. It's amazingly precise. And because they did some feature engineering. Initially, they did the forecasting only using the daily wind speed. Their data set that they got, that they had measurement of the wind speed for every 25 minutes. To convert to a daily wind speed, they got the average of the wind speed for each day. Using only this information of the average of the daily wind speed, they got those metrics, showing that the support vector regressor was the best model. But then they decided to include the standard deviation of the daily wind speed. So that says how much the wind is varying during the day. It's if it's stable or not stable. And the improvement in their metrics was really high. So they got a huge improvement just by adding one new feature. So one of the things that you're going to be looking in the future is how to do feature engineering to improve your model. Sometimes the best improvement is just to work with your features, not selecting different models. This other paper, I'm going to say that was my favorite paper to read for this presentation today, is Quantify Rooftop Photovoltaic Solar Energy Potential, a machine learning approach by Asulaini and others, 2017. And this project is actually quite interesting. It was done in Switzerland, and they are using support vector machine and the GIS, the Geographic Information System, to try to predict how much of the area of the rooftops in the Switzerland are available that could be installed solar cells. And that's how they're using the support vector machine. The results that they got, that they showed that 81% of the rooftops in Switzerland are available. I mean, it's a dead space. They don't have any chimney, anything else being used, and the people will never gonna use those rooftops. So if you install a solar cell there, you're gonna have 328 square kilometers of area where you could generate energy, and that's equivalent to 17.86 terawatts hour, or equivalent to 28% of the energy consumption in Switzerland in 2015. So by only using the rooftops, places that I like to say those are dead places, places that are not being used for anything else besides covering your head, you could generate energy. This is how they are actually using the machine learning for this project. From the GIS software or the ArcGIS, they have some buildings that they have the tag of how much of their rooftop are not being used for anything else. So this is an example. They have some structures where they have the mark here, and they calculate what's the square meters of the area where they can install the solar cells. They are going to train a model using the information of this building, like the age, the total area, how many people are living here, among other features, to predict what should be the amount of a free rooftop on buildings that doesn't have those tags in the GIS, but have those information about age, people, how many people living, and all those other features. So, and they are using the support vector machine or support vector regressor, this situation. And that's the result that they actually got. This first here, this top plot, those are the communes in Switzerland. The communes are the smallest division of, I believe that could be equivalent to a city for us. This first one is the ratio between the free space in the rooftops divided by the total area of the rooftops. And this one is just the total free rooftops. So they have a lot of areas that could be used for energy. They also made a calculation then. So it's not just install the solar cell. You also need to understand what is the sun position and how it's going to be the azimuth and the slope of the rays that are coming. So they calculated here for this specific one for the azimuth of 10 degrees and the slope of 35 degrees. And they see how much of the could be produced from the sun on those areas. And those are the forecasting for the production that you could have for each month of the year. And that's the total for the year. What would be the total production in megawatts hour per year per capita in Switzerland? So that's an amazing job. We might try to reproduce some of the methodology in here. So the last one for the renewable energy that I'd like to talk today is the significant wave weight and energy flux prediction for for marine energy applications, a grouping genetic algorithm, extreme learning machine approach by Cornejo, Bueno, and others, 2016. Uh, when you talk about marine energy, there are actually different types of marine energy, how they can be generated. Could be tidal, could be wave, could be currents. And what they are talking in this paper is about the wave energy converter. This is a methodology where they convert the kinetic energy of a wave to electrical energy by having a buoy that's going to be going up and down and generating energy in the other end. So they need basically two important parameters to know how much energy is going to be produced. Is that the height of the wave and the speed. So how fast this goes up and down. So they say that the two important parameters are the wave height and the wave energy flux. And they work here by doing a feature selection with this GGA, that's the grouping genetic algorithms, and the predictions using this extreme learning machine. This extreme learning machine, it's a type of a neural networks, but instead of doing backpropagation to calculate the weights, it's if you click here, they actually, oops, if you click in here, they actually use this Moore Penrose generalized inverse, that's a kind of a least squares, basically, to calculate the weights. So it's a different way to calculate the weights of a neural network. So if you want, you can come here and learn more about it. So they study this in the western coast of the United States, where there are 3 buoys, where the blue ones are the ones that they are going to be using for training, where they have the measurements of the wave height and the wave energy flux. And this red one is their blind buoy. So those are the predictions that they got for the wave height. They used the extreme learning machine, and they also compared with a support vector regressor. In both scenarios, they got very good predictions, how is going to be the wave height. And here in this table, they show that when you use all the features that they had, you had a poor support vector regressor. But when you do some feature selection, you actually improved a lot the support vector regressor, that it got even better than the extreme learning machine. So we might be looking in the future how to use the techniques for feature selection. And those are for the power as well, in kilowatts per minute. And it's the same results that they got here. The support vector regressor with feature selection got the best metrics. The only comment that I saw, the only observation is that when they have these high peaks of generated energy, they couldn't predict properly those high peaks. But in overall, this is an amazing prediction. So this is the resource of the third part. And now let's gonna talk how it's gonna be the learning sessions for 2021 and what to expect for this year. Those learning labs, they're gonna still be bi-weekly. So every 15 days, you're gonna have one learning labs. They're gonna be Wednesdays at 4 p.m. And our goal is try to reproduce, between quotation, the methodology of a paper. So it's gonna be hands-on. Actually hands-on from my part. You're gonna be watching. And when I say reproduce the methodology, probably is not going to reproduce the full methodology of a paper, because sometimes those papers are a full master's or PhD research. What you're going to do is reproduce parts of those methodologies. And in most of those scenarios, you're not going to have access to the data set. So we might look to similar data set or a data set that has similar properties, and I'm going to try to reproduce the methodology, see how the methodology work. So we're going to start the learning lab by presenting the paper that you are trying to reproduce, talking about which part of the methodology we are reproducing, and talking about of the data set that's not going to necessarily be even from the energy sector, but that you can use the same type of methodology. You're going to be focusing in Python, so our presentations are going to be in Jupyter Notebooks or Jupyter Labs, and the codes and all materials, they're going to be available in the Cruise website. If you click here, you can access the Cruise website, and all the material is going to be available here, so you can download everything. So those are the information from the last year Learning Labs, and they're going to be free. You don't have to register or anything. Those are open source. So that's all that I want to talk today. And if you have any questions, please, you can send a message, or now you can unmute your mic and video and you can start talking. Thank you. If you have any questions. Daniel, do you have any comments, Daniel?
Yeah, actually, I was thinking in that paper where they were the particle storm optimization, they were trying to estimate the parameters. Do you know, are they following any particular model on how to change the parameters? For example, like when we do regularization, right? If we are changing the hyperparameter between the model misfit and the norm, we know that the hyperparameters will make a very predefined movement of the connection between the two, right? We have the L curve and things like that. So I was wondering, do they use some kind of model like that in general, or is just chaotic, whatever?
Well, it was not very clear in the paper, actually. What they make really clear in the paper is how to change the position and the velocity of the bird using some random numbers, but I'm not sure how they applied these there. So I believe they just did some changes in the hyperparameter.
Mm-hmm.
So it was basically a fancier way to do grid search.
Mm-hmm.
So any other comments? Any other questions? Did someone send a chat? No?
No, yeah, didn't see anybody.
So if you don't have any questions, I'm going to stop the recording, and I'd like to thank everybody for joining, and see you in 2 weeks.
So it's on